Hi, good morning everyone, and wish you a happy Dasara. And today morning we are going to discuss on class 11. Okay, chapter number 4. The two topics are left. That topics we are going to discuss today. Okay, so welcome to the channel Density Classes, and this is Sir Kumar sir. Okay. So here, what is the first topic we are going to discuss today is overlapping. What is actually overlapping concepts? Okay, what does it means? Overlapping means what? We are going to see that. So basically, when two atoms approaches each other, okay, when two atoms are there, they are approaching each other, partial mergers of two bonding orbitals known as overlapping of the orbitals. So when two atoms are approaching each other, so there, suppose this is one atom, and this suppose two atoms are approaching each other, and this is one orbital of that particular atom, and this is another orbital of that particular atoms. So suppose S orbital. So when they approach each other, you will see that they will be merging within each others. Okay, they will be merging over each others. So this is known as nothing but what? Overlapping of a orbitals. Understood? So when two atoms will approach each others, they will merge into each others. Okay or not? And this process of merging, we call it as what? Overlapping of the orbitals. Understood? Okay, fine. Let's go to the types of overlapping. So types of overlapping, there are different types of overlapping, and in that also the first one we are going to discuss is what? Sigma bonds. Okay, now sigma bond is formed how and which type of overlapping is involved here, we are going to see to it. Okay, sigma bond, it is represented like this. Okay, so what is sigma bond? It is formed by the end-to-end head-on overlapping of a bonding orbitals. Okay, this sigma bond is formed by the head-on overlapping. Head-on overlapping is this one. Suppose this is one orbital and this is another, so they will be overlapping this way. This is called as head-on overlapping, or we call it as end-to-end overlapping. Got it or not? This way. Got it? So it is formed by the end-to-end head-on overlapping of a bonding orbital along the intermolecular axis. Along the axis, intermolecular axis. Intermolecular axis means this is the intermolecular axis, so they will be overlapping this way. Okay or not? So this kind of when the bond is formed in this manner, when the bond is formed by the head-on overlapping, that bond we call it as what? Sigma bond. Okay. Okay, now types of head-on overlapping. There are head-on overlapping also. There are three types we are going to see. The first one is SS overlapping. Okay, so SS overlapping means what? One S orbital and another S orbital, when they approaches each others, okay, then the orbitals will try to overlap with each others, and this process of overlapping we call it as SS overlapping. Okay, got it? And this is the overlap regions. Okay, this is the common region, that is overlap regions. Got it or not? Okay, and how much bigger this regions of overlapping will be, that much strong the bond will be. Okay, dear students, again I'm telling you, the more the region of overlapping, the more will be the strength of the bond. Okay, next, second one is what? Sp overlapping. Sp overlapping, you see here one orbital is S and another orbital is P. So when they are overlapping, this is S orbital and this is P orbitals. Okay, so when this S and P orbitals they are overlapping with each other, they will lead to the formations of which bonds? Sigma bonds, and the overlapping is called as Sp overlapping. This is Sp overlapping. Okay, okay, so this is Sp overlapping. The last type of head-on overlapping is PP overlapping. Okay, so one P orbitals and another P orbitals, when they overlap along the axis, they will be forming what? PP overlapping. Okay or not? And always remember, the overlapping in which there is more number of overlapped regions, that one will be stronger. Okay, so you can pause the video and you can take it down. Yeah, so we are going to discuss now pi bonds. Okay, So pi bond is what? It is the covalent bond formed. It is a covalent bond, okay, formed by the sidewise overlapping of half-filled atomic orbital, okay. So this pi bond, first of all, it is formed by the sideway overlapping, this way overlapping, okay. So pi bond is the covalent bond which is formed by the sideway overlapping of the half-filled atomic orbitals. Those are orbitals which are half-filled, okay. For example, I will tell you, this is capacity here in this orbital is 2, but it is only 1, and this orbital capacity is 2, but here it is only 1 electron. So these two will overlap with each other. This is half filled, so they will give rise to the formation of what? Pi bond, okay. So atomic orbital of the bonding atoms, it is called as lateral or sidewise overlapping, okay. Lateral overlapping or sidewise overlapping. So see, this is one orbital, this is another orbital, so they are overlapping. This is sideways, they will overlap with each other. As a result, the regions of overlapping is very less here. The region of overlapped region will be less, okay, will be less. Got it? Here the overlapped region will be less. As a result, this pi bonds which is formed, it will be weaker comparing to the sigma bond, okay. So now let us see the difference between sigma bond and pi bond. See, pi bond, it is formed by the head-on overlapping, whereas sigma bond, it is formed by the sidewise overlapping, okay. Second point, in it the region of overlapping is more. In pi bonds or sigma bond, you will find that the region of overlapping is more. As a result, they are strong bond, whereas in pi bond the region of overlapping is less. That's why they are considered as weak bond. In sigma bond, it is a stronger bond, whereas pi bond, it is less stronger than the sigma bond, okay. So these are some few differences between sigma and pi bond. Got it? So we have written it. So this was basic introductions about pi bond, sigma bond, and type of overlapping. Now let us move on to the next topic, okay. You can pause the video and take down. Okay, dear students, so now we are going to see hybridization. What is hybridization and all? So basically, hybridizations, what it is? It is the process of intermixing of an orbital, okay. Only those orbitals, suppose this is s orbital and this is another s orbital, okay. So when they are intermixing, this is called intermixing, okay. So the process of intermixing of orbitals of slightly different energy, this orbital and this orbital, the difference in their energy will be very less, okay. They will be having almost same energy. That means only difference will be the difference between the energies of these two orbitals will be small. That's what very important it is, okay. The process of intermixing of the atomic of the orbital of slightly different energies so as to redistribute the energy, resulting in the formation of new sets of orbital of equivalent energies, okay. So these two orbitals which are hybridizing, their energy differences should be less. If the energy differences is high, they cannot undergo hybridization, and redistribution of energy can't be taken place, okay. So always remember, hybridization is an intermixing process of the orbital of slightly different energy, so that the redistribution of energy, okay, so that there will be a redistribution of energy in the resulting, okay, there will be a redistribution of energy resulting in the formation of a new sets of equivalent energies orbital. Got it or not? So this is called as what? Nothing but hybridizations, okay. Now what are the characteristics of hybridizations? Let us see. Characteristic of hybridization, number one is what? The number of hybrid orbital is equals to the number of atomic hybrid orbital or number of orbital hybridized. Means what? Suppose here two orbitals are hybridized, then the number of hybridized orbital you will get is 2 only. The number of hybridized, DISGD, number of hybridized orbital is equals to the orbital hybridized, okay. Number of the hybrid orbital, how many orbitals are hybridizing? 2. So number of hybridized orbital also will be 2. If 3 are hybridized, then number of hybridized orbital will be 3. If 4 are hybridized, the number of hybridized orbital will be 4. Understood? That is the meaning, that is the first characteristic of hybridization. How many orbital are hybridizing? Same number of hybridized resulting orbital will be same. Okay. Number 2, the hybridized orbital hence have equal energies and shape. The orbitals which are going to hybridize, they will have equal energy, okay, and shape as comparing to the hybrid orbitals. Okay or not? Third point, the hybridized orbital is more effective in forming stable bond. The hybridized orbital, the orbital which we are getting after intermixing of two orbitals, that will have what? That will be having more effective. They will be more effective in formation of a stable bond. That means the hybridized orbital, they will lead to the formation of a stable bond. Okay. So these are the 3 characteristics. In short, I have given you. These are the 3 characteristics of what? Hybridization. Now let us go to the conditions of hybridization. Actually, if you see properly, there are 6, but I have given you only 3. Okay, if these 3 properly, if you have learned, that will be enough. Okay. Condition for hybridizations: only the orbital present in the valence shells. Okay, only those orbitals present in the valence shells, they participate in hybridization. Okay, only the orbital present in the valence shell of the atoms are hybridized. Only those orbitals which are present in the valence shells, they will be taking part in the hybridization. Valence shell means outermost shell jiman electron থাকিব নহলে orbital থাকিব উটো খানহি participate কৰিব in the formation of bond. Okay. Second point, the orbital undergoing hybridization should have small energy difference. Suppose this is s orbital and this is another p orbital, so the energy difference between these 2 orbitals should be almost near to each other. The energy difference should not be very huge in between them. If the energy difference between s orbital and the p orbital is very huge, they cannot hybridize. The energy difference should be very small. Okay, near to each other it should be, then only it will be hybridized. Okay. Third one is promotion is not an essential condition prior to hybridization. Okay, so promotion is not an essential condition means what? Whenever we see the electrons gets excited, so the electron jump from one level to another level, that is not necessary. Okay, before the hybridization, it is not required that promotion of electrons should be there. Okay, it's not at all essential. That is what it is said in the third conditions. So hope, dear students, what is hybridization, characteristic of hybridization and condition of hybridization, you have understood. Okay, got it? So if you have any doubt, you comment in the comment box so that I can clear your doubts, and for now you can pause the video and take down the notes. Okay. Okay, dear students, now we are going to discuss type of hybridization. Very important. Okay, have to try to understand properly, because from this sections you will get a questions in your board exam. Sometimes it comes for 5 marks, sometimes for 3 marks. Okay. So types of hybridization. The first type is what? Sp hybridizations. Okay. So in Sp hybridizations, how many s orbital is combining? The s orbital which is combining is 1, and the p orbital which is combining is 1. Okay, the combination, the head-on overlapping is taking place along z-axis. They are overlapping this way. Okay, so the head-on overlapping is taking place along the z-axis, in which one s orbital and one p orbital, they are participating in hybridizations or in overlapping. So after the overlapping, you will see that all the this is called as a lobes. Okay, this is called as lobes. Okay, got it or not? So this is positive lobes, this is negative lobes. Okay, so after the hybridization, you will see that both the lobes, okay, they are equal in size. The positive lobes will be bigger, and the negative lobes, here you can see negative lobes. For these lobes, since it is hybridized, so you will have a small hybridized orbital will be smaller, and it is negative here. This lobe is also hybridized, so the hybridized orbital will be bigger, and the lobes which is hybridized, it will be smaller. So any lobes, if it has, like before hybridization, both the lobes will be same in size, but after hybridizations, one lobes will be bigger and other lobes will be smaller. So one lobe is bigger, another is smaller, one is bigger, another is smaller. Okay, so that shows that both the lobes are hybridized. Okay, so when they are hybridized, you will see that the positive positive sides occupy, the positive lobes is bigger in size and the negative lobes will be smaller in size. Okay, got it? So we will be writing what are the things related to it. So Sp hybridization has 50% S character and 50% P character. That means these hybridized orbitals, it will have 50% of S character and 50% of P character. Why? Because one is S orbital, another one is P orbital, so 50-50 characteristic they will have. Okay, these two Sp hybrid orbitals, this one, okay, two Sp hybrid orbital point in opposite direction along z-axis. So they are pointing in opposite direction along z-axis. The hybridization has taken place, the overlapping has taken place along z-axis, and they are pointing it in the opposite direction in the z-axis. Next, with the bigger positive lobes and a very small negative lobes. So the bigger lobes are what? Positive, and the smaller lobes are what? Negative. Again, I'm telling you, when the orbitals are hybridized, before hybridizing, they will have equal lobes, positive, negative equals. But after the hybridizations, you will see that one lobes will be bigger, another one will be smaller, and in opposite directions. These two hybrid orbitals have linear hybridization, so their structure is what? Linear. They have linear shapes. And what is the bone angle here? Bone angle is 180. And if you look at, then BEF2 also will have same kind of hybridization, same kind of structures. Okay, so in the exam, if you are asked on the basis of hybridization, draw the shape of BEF2, then you have to draw it in the same manner. Got it, dear students? Okay, fine. If you are done, good. Next, we are going to move on to the Sp2 type hybridizations. Okay, pause the video and take down. Okay, dear students, now we are going to do Sp2 hybridizations. Okay, this is very important, and in the exam, how they used to ask questions, we will discuss on that also. Okay, it comes for 5 marks. Okay, so dear students, you have to understand it properly. So in Sp2 hybridizations, what will be there? It consists of one S orbital and P orbitals are 2. See, here it is written Sp2, so S orbital is 1 and P orbital is 2. So that's the clear, I think. So here S orbital, and this is 2 P orbitals. Okay, now one is along axis is along z axis, one axis is along y axis. Okay, so now when these three orbitals, they will intermix, they will combine with each others, so they will be like this. So this orbital is this way, this orbital is this way, and this is circular one, right? So S orbital is this one, circular one. This is called intermixing of an orbital. After intermixing process is over, then you will get a hybridized orbital. Okay, so how many orbitals are combining? 2, 3. 3 orbitals are combining, as I have already told you in the characteristic of a hybridization, that how many orbitals will combine? Same number of hybridized orbital will be produced. So you see here 1, 2, 3. 3 hybridized orbitals are produced, and all the 3 orbitals are hybridized. How we know? Because you see positive lobes is bigger and negative lobes is smaller for this. Positive lobes is bigger for this and negative lobes is smaller. Here positive lobes is bigger and negative lobes is smaller. So all has one positive lobes bigger and negative lobes is smaller. That indicates that these 3 hybrid orbitals are being hybridized. If both the lobes are of same size, then you should understand that the orbital is not hybridized. Okay, if it has one small, one big lobes, then you can clearly state that particular orbital is hybridized. So this is Sp2 hybridizations. Okay, so this is a hybridized orbitals. Okay, we can call it as hybridized b orbitals. Okay, got it. So what are the features of this Sp2 hybridization? Here you will see it has 33.3% of S character. This hybridized orbital, it will have how much S character? 33.3% S character, because only one out of the three, only one part is S. So 33.3% it will have S character, and 66.7% it will have a P character, because out of the three, two parts are P orbitals. So they will have P characteristic more. Fine. It has a trigonal planar structure, so the structure is trigonal planar, and in it one S orbital and two P orbitals are participating in the hybridization. So these points are clear. The and angle is what? Bond angle. This angle will be 120 degree. So always remember that angle is 120 degree. Structure is trigonal planar structure. Okay, now let us try to understand with these examples with Sp2 hybridization process. We will take one example and we'll try to see the formation of that particular compound. So questions in the exam, it will be asked, on the basis of hybridization, explain the formation of BCl2. Got it? Explain the formation of BCl2. So in this kind of questions, what you have to do, first of all, you have to write in this the central atom is what? Which one is the central atom? B will be the central atoms. Already I have told you Lewis dot structure and all. So you might not be having the problem in identifying the central atoms. Okay, so here central atom is B. So you will write here in this the central atom is B. B का electronic configuration is what? 1s2, 2s2, 2p1. मतलब atomic number is boron का 5. So boron in the ground state. Ground state means normal state in which they exist. Okay, no? Normally without any extra energy or any modification. Normally in which state they exist, that is called as a ground state. So ground state, you can see that 2s and 2p is the outermost shells. So we have already seen that the outermost cells, that is valence shells, participate in hybridization. So this is innermost cell, they will not participate. This two is the outermost cells, they will be participating in the hybridization. So here 2s, how many electrons are there? 2. So we have written one electron like this, one electron this way. Both should be opposite. Okay, one is towards up, down, then one will be towards up. Okay, like this we have to represent it, because it represents the orientations of the electrons or the spinning. Okay, so one box capacity is 2 electrons. Okay, so 2s, s orbital only 2 electrons, so 2s, one box. Then 2p, p ka capacity is 6, so boxes will be how much? Orbitals will be how much? 3, 1, 2, 3. So here it is in the ground state, 2s it has 2 electrons and 2p it has 1 electrons. In the excited state, B5 in the excited state promotions of these 2s electrons will take place. These electrons, 2s electrons, it will be promoted to 2p, so it will be 1, 1, 1. So 2p now has 2 electrons and s has 1 electrons. So this is the unpaired electrons, right? We have already seen in the characteristic of hybridizations, half-filled orbital participate in hybridization. So these are all half-filled orbitals, and this is the hybridized borons orbitals. Okay, this is the hybridized borons orbitals. So we have written here boron hybridized orbitals. Now these hybridized orbitals of 3 hybridized orbital of boron will overlap with chlorine. Chlorine, how much it is there? BCl, I think it should be 3, BCl3. Yeah, it is BCl3. Okay, so Cl ka, if you see properly, Cl last electron enters in which orbital? In Cl, if you see p orbitals, right? 5 is there. 1, 2, 3, 4, 5. Only the last one is left single, right? Others all are paired. So this last one here, this is for chlorine 1. Then chlorine, how many are there? 3. So this chlorine 3, it will be overlapping. Okay, chlorine 3. So you will see here 1, 2, 1, 2, and here it will be single. So these last orbitals Okay, they will participate in hybridization. See here, since they belongs to p orbitals, so we have drawn the p orbitals here. So they are overlapping with the hybridized boron orbitals. 3 boron hybridized orbital will be there. That hybridized orbital will overlap with the 3 p orbitals of borons. So when the hybridizations will take place, this is what? Head-on overlapping. So they will form a sigma bond. Sigma bond they have formed, leading to the structure of what? Trigonal planar, and the bond angle is 120 degree. Okay, so these things, if you have to learn it properly, okay, got it? I have explained to you in short, so you have to learn it properly so that you will do well in your examinations. Very important, dear students. So you have to try to understand properly, and if you are not understanding one time, watch the video again and again so that you understand it properly. Okay, got it? So pause the video and take down. Okay, students, so last type of hybridizations we are going to discuss. Again, of course, many are there special types of hybridization and all. That one we are not going to discuss. So last type of hybridization which we are going to discuss, third number, is Sp3 hybridizations. Okay, so in Sp3 hybridizations, you can see clearly here S is 1 and P is 3. That means S orbital here, participation of S orbital is only one S orbital will participate. And how many p orbitals are participating? 3 p orbitals are participating. The p orbital which are participating is, this is along z axis, this is along x axis, and this is along y axis. So 2pz, 2px, 2py. So these are the 3 z orbitals, or sorry, 3 p orbitals which are participating in the hybridizations. So you will see that when they all have energy difference very small in between them, so that is why they are hybridizing. They are going to hybridize with each other. Okay, so when they will be hybridized, then you see here one is here, another, see, this is along x-axis, this is along z-axis, this is along y-axis, and this is the s orbital, the circle. So this is called as what? Intermixing of orbitals. So here intermixing of orbital will take place. That means hybridization will be in process here. Okay. Okay, after the intermixings, they will be hybridized. So when they are hybridized, as I told you, the best way to identify whether it is hybridized or not, you have to see the lobes. If one lobe is positive and if one lobe is big and other lobe is small, that shows that the orbital has been hybridized. So here how many orbitals are there? 1, 2, 3, 4. So see here, one positive, opposite is what? Small lobes. So that means this is hybridized. Another one, this is positive, another side you see a small lobe, it is hybridized. This is positive, another side you see a small lobe is there, negative, hybridized. That means all the 4 orbitals are hybridized. Now if you connect it, all these structures, you will see that the structure, this structure which we are getting, we call it as what? Tetrahedral structure. And the bond angle of this tetrahedral structure is what? 109.5 degree. 109.5 degree is the bond angle. Okay, some example of Sp3 hybridization is Ch-04, NH3, H2O. So basically this is asked in your exam for 5 marks or 4 marks, okay, in the exam. So we are going to discuss after this. I will discuss with you these hybridized orbitals. Now it will it will be undergoing hybridizations with others. We will discuss it. Okay, so what are the characteristics here? We have s orbital only one participation, and 3 p orbitals are participating in the hybridizations. That one I have told you. Here the characteristic of s orbitals, the characteristic of the hybridized orbitals, it will have only a 25% s character. This hybridized orbital will have only 25% s character, and 75% it will have p character. Its structure is tetrahedral and the bond angle is 109.5 degree. Okay or not? So this is about your Sp3 hybridizations. Now these hybridized orbitals, again it will be overlapping with other things we are going to discuss. Now in the next after this, you take down, we are going to discuss the shape formation of Ch-04 on the basis of hybridizations. Okay, got it? So pause the video and take it down. So dear students, this is the questions how it is asked in the board exam. Explain the formation of Ch-04 on the basis of hybridizations. So first of all, we have to identify here central atom. Central atom will be carbon. So right here the central atom is carbon, C. Okay, so carbon in the ground state, we will write it. Okay, carbon in ground state. So ground state, if you see the electronic configuration of a carbon, so first of all we will write carbon, the electronic configurations of carbon. Carbon C6 equals to 1s2, 2s2, 2p2. So this is the electronic configuration of carbon. So we'll write here carbon in ground state. Carbon in ground state. So ground state, what is the, as I have already told you in the beginning of this hybridization, that only the valence orbitals will be participating in the hybridization. So innermost will not participate, outermost only. The outermost is 2s, 2p. Okay, so outermost will be participating. So we'll write here 2s, it can accommodate only 2 electrons, so only one box orbitals, and p can accommodate maximum 6, so there will be 3 boxes, 2p. So you see here, there how much 2s is having, how many electrons? 2 electrons. So we'll write it here 1, 2. And how many p orbitals are having electrons? 2. So we'll write it here 1, 2. First of all, you have to fill single, then after that you will have to pair it. You cannot write one in the one box 2 together. First go singly fill it, and then you pair it up. Okay, now carbon in excited state, what will happen? The electrons will jump to the next, these electrons in the s orbital, it will jump to the next higher level, that is called as promotions of electrons. Okay, so here you will have 1 electron, here 1, 1, 1, so 2s, 2p. Got it? So this is excited state. Okay, got it? Now what is that? H is there, right or not? Ch4. So Ch4, H ka, if you will see, if you will see the H ka orbitals, then H ka orbital, it will be like this: 1s, here it will be 1 electron, 1s, another H will be 1s, and another electrons, again you will be seeing that there will be 1 electrons, 1s, and another electron orbital will be 1s, 1 electron. Okay, so when these carbons electrons, outermost electrons, they become hybridized. Okay, they are all half filled. So when they will become hybridized, with these hybridized orbitals, one hydrogens will come and pair up. Okay, 1 hydrogens will come and pair up with here, 1 hydrogens will come and pair up here, 1 will come and pair up here, 1 will come and pair up here, overlap. Okay, they are also half filled, they are also half filled, so they will overlap in order to form a sigma bonds. And the overlapping, since it is all s orbitals, so the overlapping will be what? Head on overlapping or end to end overlapping. As a result, they will form a sigma bond. So let us see how it will be. Okay, this is the hydrogens. So we have already seen that the hybridized carbon atom orbitals is how, like this, positive, then it was like this, positive, then it was this way, positive, and there was one more positive. So this was the hybridized carbon atoms. Okay, these hybridized carbon atoms, when it will be added with, how many unhybridized hydrogen atoms are there? Ch4. So 4 s orbitals. Okay, 4 s orbitals. All the hydrogen, it has only 1 electron, so it's all occupies which orbital? S orbital. So 4 s orbital, when they will be hybridizing together, then you will see that it will be like this. Yeah, this is positive, 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 positive. Here it will be s orbital, hydrogen. Here it will be s orbital. Here it will be s orbital, hydrogen ka, and this is the hydrogen ka s orbital. So all the hydrogens, it will be overlapping with the hybridized orbital of carbon. Okay, this is 4 hydrogen orbitals. Okay, this is 4 hydrogen orbitals, hydrogen s orbital. Okay, 4 hydrogen s orbital, and this is called hybridized orbital. Okay, hybridized carbon orbitals. So they hybridized carbon orbitals, they will combine with unhybridized hydrogen orbitals like this, and when they do so, they will give us a structure like this. Since this is a head-on overlapping, so they will form what? Sigma bond. So this is hydrogen is forming sigma bond with carbon, so leading to the formation of this structure, and here bond angle will be 109.5 degree, and this structure we call it as what? Tetrahedral structure, and this is the tetrahedral structure of Ch-4. This is how Ch-4 will be formed on the basis of hybridizations. So this one you have to understand it properly, dear students, and similarly you will do for water and for the NH3. Both is important. I am telling you again, it is important. Both are important. You have to practice at home. If you are not able to do, you tell to me. Okay, I will help you out. Got it? So this one I hope you have understood, so you can take it down. Got it? And please practice it properly, and you have to explain the formation of Ch-4 on the basis of hybridization. So whatever things we have done, you have to put it in your own words. You have to write here the central atom is carbons, and carbon electronic configuration is like this, and the ground state it is this way, and the excited state this one electron gets promoted to p orbitals, and 4 unhybridized orbitals of hydrogens will be overlapping head-on with the 4 hybridized orbital of carbons, leading to the formations of tetrahedral structures with a bond angle of 109.5 degree. So this is how the formations of methanes takes place. Got it or not? So you have to put it in your words. This theory part, conceptual part, I have written it. You can write it, and this is very important for your board exam. Not only this, Ch4, H2O and NH3, this all will have same structures, so all of you should practice H2O and NH3. Okay, and another one is a little advanced type, that is ethene structure and ethane structure on the basis of hybridizations. So all of you have to practice this. If you have doubt in it, then you can comment in the comment box. I will do it for you in the next videos. Okay, so here we come to the end of advanced hybridizations are also there. Okay, unique properties of hybridization, that one we are not going to discuss. We are going to discuss now M.O.T, next topic. So pause the video and take down. Okay, the last topic of this chapter, chapter number 4. Let us see what is it. Okay, so the last topic is what? Molecular orbital theory. This is also very important for your exams. Generally it comes in CBSE as well as NBSE. It comes for 5 marks. Okay, dear students, so this is one very important, and something like hybridization, VSCPR and M.O.T. Out of these 3, very important it is. Out of these 3, 1 sure to come in your board examination, or 2 also may come as a choose optional. Okay, which one you want to do. So listen very carefully and try to understand. Okay. So molecular orbital theory. So we are going to discuss some features of molecular orbital theory, and how the molecular orbital theories are formed, or how the molecular orbitals are formed, and what are the silent features of these molecular orbitals. We call it as M.O.T. We are going to see it. So the first features is what? Like electrons of atoms are present. When in an atom, you will see that electrons are present in what? Atoms are present in atomic orbitals. Okay, suppose there is one atom. Okay, so atom is there, so the positive charge will be here. Electrons will be present in what? This orbit. So this is called as what? Atomic orbital. Okay, atomic orbitals. So like in an atoms, electrons are present in atomic orbitals. Similarly, in molecular orbitals in molecules, the electrons are present in what? Different molecular orbitals. Like electrons of an atom is present in what? Atomic orbitals. Electron in a molecules, okay, electron in an atom is present in atomic orbitals, okay, and electrons in a molecules are present in different molecular orbitals, okay. So from here you can differentiate between atomic orbital also and molecular orbital also. Both the differences also you can see, as well as the feature also. So 2 in 1 this is, no need to write the differences between them separately, so you can understand from here itself, okay. So in atomic orbital you will see that in atomic orbital electrons are present in an atoms in an atomic orbital, whereas in molecules the electrons are present in molecular orbitals. Okay, point number 1 is clear. Next, molecular orbitals are formed by the combination of atomic orbitals, okay. When one atomic orbital, suppose this is one atomic orbitals, okay, this is one atomic orbital and this is another atomic orbitals. When these two will be combined with each other, in proper symmetry, and they should have comparable energy, okay. Comparable means the energy differences between them should not be too much, okay. So when they are combined, when atomic orbitals of this merges to molecular orbitals, so molecular orbitals are formed by the combination of atomic orbitals, okay, of proper symmetry and comparable energy difference. Their energy difference should not be that too much, it should be small. The energy difference between the two atomic orbitals which are going to combine should be small, okay. So when they combine it, they merges into a molecular orbitals, okay or not? Got it? When two atomic orbitals of comparable energy and proper symmetry combines together, they merges into a molecular orbitals. So they will be combining, so they will be merging into a molecular orbital. This is called molecular orbitals, okay. Got it? Okay, fine. So as the electron in atomic orbitals are under the influence of only one nucleus, so as we have seen, this is an atoms, okay. So here the electrons, all the electrons will be under the influence of only one nucleus, right or not? But electron in molecular orbitals, they are under the influence of 2 or more nuclei depending upon the number of atoms, okay or not? But in molecular orbital you will see that single electrons may be under the influence of 2 or more atoms, or 2 or more nuclei, okay. Depending upon the number of atoms present, how many number of atoms are present, that much nucleus will be there, and that much influence, or the electron, single electron may have that much influence of nucleus, okay no? Okay, so fourth point is what? The number of molecular orbital formed is equals to the number of combining atomic orbital. So see here, this is combining atomic orbital, this is atomic orbital, okay. This one is atomic orbital. So how many atomic orbitals are there? 2 atomic orbitals are there. So molecular orbital also will be formed is 2. So one molecular orbital formed down, that is called bonding molecular orbital. This is called as a bonding molecular orbital, and another molecular orbital will be formed up. This is called as a anti-bonding molecular orbital. Got it? This is called anti-bonding molecular orbitals, okay. So 2 molecular orbital combines, sorry, 2 atomic orbitals combined, they will give 2 molecular orbital. One is called as a bonding molecular orbital, and another one is upper one, we will call it as anti-bonding molecular orbitals. So these are some features of molecular orbital theories, 7 features, okay. You can take it down, and this one you can use it for writing the difference between molecular orbital and atomic orbital as well. Hope you have understood, dear students. Very important topics we are doing, okay. So take down. Okay, dear students, so now let us see how these combinations and all it takes place. Let us try to understand with simple examples, okay. So according to linear combination of atomic orbitals, okay, it is said that the electrons, they have that all the atoms or the electrons present in the atoms, they have a wave functions. They can be represented with the help of a wave functions, okay or not? So let us consider the H2. H2 is a molecules, right? So let's consider that in H2 there are how many hydrogens? 2 hydrogens are there. So one hydrogen is A, another hydrogen is B. Okay, one atom of hydrogen is A, another hydrogen atom is B. Okay, got it? Understood? So let's assume that, okay, the wave functions of these electrons is phi A, and the wave function of these electrons will represent by a wave function this way. Got it? So always remember, if we have said that the molecular orbitals are formed by the combination of 2 atomic orbitals. Okay, so let us write so formation of formations of molecular orbitals formation of molecular orbitals by additions, okay, by additions of formations of molecular orbital by addition of wave functions. So by addition of wave functions, so when the wave functions are added, it will the formation of molecular orbital by addition of wave function is called bonding molecular orbitals. So when there is a formation of molecular orbital by addition of wave function, that one we call it as what? Molecular orbitals, bonding molecular orbitals. For example, you can write here these symbols, wave functions ka. So wave functions molecular orbitals is equals to what? By A plus wave function of B. So when there is additions of the wave function of A and B, it leads to the formation of bonding molecular orbitals. Bonding molecular orbital is represented by sigma. Sigma is equals to, okay, wave function of A plus wave function of B. This one you have understood? Okay. Similarly, formation of molecular orbital by subtractions, okay, subtractions of wave functions. Subtraction of wave function is called what? Is called antibonding, okay, is called antibonding MO, okay. It is called as the antibonding molecular orbitals. So that one will write it as wave functions molecular orbital equals to wave function of A minus wave function of B. Okay, got it? So it is represented by sigma star. Okay, always remember antibonding molecular orbital is represented by sigma star, wave function of A minus wave function of B. So this is called as a antibonding molecular orbitals. So I hope, dear students, you have got it. Okay, I have taken an examples of linear combination of atomic orbitals in hydrogen molecules. So I have considered one atom of hydrogen as A, another atom of hydrogen as B. The electrons, okay, which is present in the hydrogen atom can be represented with the help of wave functions. So we have written it as here wave function of A, and this one we have atom B, we have written the wave function B. So when we add the two, when we combine the two wave function of A and B, two atoms, when there is an addition of wave function of two atoms, then that bonding molecular orbital is called as addition molecular orbital, or is called as bonding molecular orbitals. And when there is a subtractions of wave functions of atom A and B, then that is called as what? Antibonding molecular orbital. It is represented by sigma star. Okay, so you can take it down. Okay, dear students, so we are going to learn now how to draw a molecular orbital diagram of N2. Okay, molecular orbital diagram, and related to this many things are there which we will be discussing now. Okay, so we are going to draw for N2, and remember, for the diagram is same for N2, C2, B2, Le2, Be2. That's why I have written in the bracket. Okay, all I will not be doing again and again. So I'm doing it for N2, and generally N2 comes in your board examinations. Okay, so of course C2 B2 also you draw it in the same way and try to fill in the electrons. It will be easy, it is easy only, same structure. All these molecules, they have the same kind of molecular orbital diagram. So let's start. This is the energy level. From here we are going from lower level to the higher level. Okay, so this is what one nitrogen atoms, and this is another nitrogen atoms. This side it is all nitrogen atoms ka. And in the middle one you can see this middle part, it is molecular orbital, that is N2, two nitrogen atoms combines together giving us molecular orbitals. Okay, this is atomic orbitals. So let us start. First, this one is what? 1s. First electron, here it is 1s. So we'll write here 1s, here it is 1s. So 1s, how much? 2. So 2 electrons, we'll write it here. 2 electrons, we have written it here. So as we have seen, when there is the additions of the electrons, they lead to the formation of bonding orbitals. So bonding orbitals, it is more powerful than anti-bonding. So one electrons, this 1s, it will give 1 electrons here, and this 1s, it will give 1 electron for bonding orbitals. So they will form like this. Okay, this is called as the bonding orbitals, and it is represented by sigma, and here it is sigma 1s. Got it or not? So we'll write it sigma 1s. How many are there? 2. So we'll write sigma 1s 2. Next, 1 electron is left here, 1 electron left here, so that one will be taken away by whom? Anti-bonding. So anti-bonding, it will be taking away the electrons. So here this is called as what? This is formed by the subtractions. So this one, it will be called as what? Sigma star, as I have already told you. Sigma star 1s 2. So this is all 1s. So done. Molecular orbital for 1s is formed. Okay, fine. Now coming to the next is what? 2s. So we'll write here 2s, and here it will be 2s. How many electrons are there? 2 electrons. So 2 electrons here, 2 electrons here, also 2 electrons. So we have written done, done. This one we are done, done. Okay, so now again same thing, 1 electrons will be given from here, 1 electron from here. So it will be forming us what? Sigma 2s2, and here it will be sigma star 2s2. Okay, so this is molecular orbital formed for 2s orbitals. Now 2p. 2p is how much? 3. So 2p, 3 means 1 electron here, 1 electron here, 1 electron here. Similarly, 1 electron here, 1 electron here, and 1 electron here. So both the atomic orbital, I have filled it with 3 electrons each. Now what we have to write? Now 1 electrons will be given from here, and 1 electrons will be given from here. Done. 1 electrons will be given from here, and 1 electrons will be given from here. So done. Now 1 electron left here, 1 electron is left here. So that one it will be giving here. Is there any more electron left for anti-bonding? No electrons left. So anti-bonding will be vacant here. Okay. So we'll write here sigma 2pz, sigma this is, sorry, sigma pi 2px, pi 2py. This is pi 2px, pi 2py, and this will be sigma 2pz. Yeah, so similarly here it will be written as pi star px 2 2. Okay, and here it is nothing, so just no need to write. Pi star 2p x is this one, 2px, this is 2py, and sigma star 2pz. So this is the molecular orbital diagram for nitrogen. Very simple it is, just you have to keep it in mind the structures, and as we go higher, energy is increasing. Okay, so here anti-bonding will remain what? Vacant, because there is no electrons to be given to this. Okay, now if I want to write, I hope you have understood this. Very simple it is, but very important, extremely important for your board exam. Last 3 years it has been repeated in the board examinations for 5 marks. Okay, so very important one. Okay, now one thing, dear student, if you are asked to write electronic configurations of M.O. molecular orbital diagrams, if you are asked to write electronic configuration of molecular orbital diagram, then how to write the electronic configuration for this molecular orbital? So we'll start from here. What is here? Sigma 1s2. So we'll write sigma 1s2. Next is sigma star 1s2. So we have written next is what? Sigma 2s2, sigma star 2s2 written. Next is what? Pi 2p x2, pi 2p y2, and sigma 2p z2. Okay, got it? Sigma 2p z2, and then you will be writing here pi 2p x star equals to 0. No need to write, you can write up to here only. Okay, no need to write this 0 part. Okay, only up to where the electron is filled, up to that you can write. So this is electronic configuration of molecular orbitals. Got it, dear students? You have to start writing from here in the sequence. That is the molecular orbital, electronic configuration of molecular orbitals. Now next things they ask in the exam is their magnetic behavior. So magnetic behavior will be what? Magnetic behavior. So magnetic behavior, dear students, is equals to all you see, all are paired up, or all the molecular orbitals are paired up. So all the molecular orbitals are paired up, then the magnetic behavior is diamagnetic. If there is any unpaired electrons in the molecular orbital, in the middle one, I'm talking about middle, not the side. Okay, side you forget it. Middle one is molecular orbital. If there is any unpaired electron here in the middle one, then we call it as magnetic behavior as what? Diamagnetic. Since it is all paired, so it will be called as diamagnetic. Okay, now next thing they are asked what? Bond order. So bond order is equals to number of bonding orbital. Okay, bonding orbitals, number of bonding electrons minus number of anti-bonding divided by 2. So number of bonding electrons are how much? Bonding electron all the down 2, 4, 8, 10. 10 is there. Anti-bonding upside 2, 4. Only 4 is there. So 4 divided by 2. So how much it comes? 6 divided by 2. So bond order is 3. Number of bonding orbital electrons minus number of anti-bonding electrons divided by 2, that will give you the bond order. So these are the 3 things along with the diagram which they ask in the exams for 5 marks. So dear students, please you can watch the video properly and try to understand it properly so that you don't make mistake in the examinations. Okay, so thank you students. Now we will be going to the next one. One more is there, different type, that is oxygen ka. I will draw it. So by the meantime you can pause the video and take it down. Diagram of O2. So O2 molecular orbital diagram of oxygens, molecules of oxygens and fluorine and neon, it is same. Okay, so I have written here O2, F2 and Ne2. So F2, Ne2 you can try at home. O2 I am going to show you how to do it. O2 ka. Okay, so see here one oxygen atom we have written, and on the left one oxygen atom, on the right one oxygen atom. Their electronic configuration is what? 1s2, 2s2, 2p4. And on the right also we have written 1s2, 2s2, 2p4, and in the middle we have written MO, that is molecular orbitals, and here we have written here what? O2. Got it? Both the oxygen 1, oxygen 2, it will combine together, it will give us O2, and this line indicates the energy level, energy. That energy is increasing from the bottom to the top. So first is what? 1s. So we have written 1s, same 1s, we have written 2 electrons here, 2 electrons here. Then 1 electrons will be coming from 1s here and 1 electron from here, so it will be giving us sigma 1s2, and remaining 1 electron left here, that one will be going to the anti-bonding, it will be giving us sigma star 1s2. Next 2s, 2 electron is there, 2 electron here, so 1 electron from left side, 1 electron from right side, it will be coming to form a bonding orbital sigma 2s2, and left out 1 electron, so it will be coming to the anti-bonding to form a sigma star 2s2. Okay, fine. Now what we are going to do, now P, there is 4 electrons here, so we have written 4 electrons here, 4 electrons here. So how the combinations will be taking place? 2pz. So first 2pz will be filled. So 1 electrons done. Then 2px it will be filled, 1 electron done. Now you can see clearly that 1 electrons here it is left in the 2px and 1 electron here it will be left. So that electrons it will be going to where? Sigma star 2pz. So 1 electrons from here it will come here, this is left out one, and 1 electron from here it will be coming here. First they have to be filled singly, then only they will be paired up. Only 1 electron is here, so here and 1 will be here. So this is the molecular orbital diagram of oxygens. Now we will write the electronic configuration. So electronic configurations we are writing same here, 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2. Then we will be writing here sigma 2pz2 electron, then pi 2px2 2py2. Then we'll write here pi star 2px1 pi star 2pzy1, and 2pz it's not there, so we will not be writing. So this is the electronic configuration of molecular orbital. Then magnetic behavior, as you can see here there is unpaired electron, so magnetic behavior will not be diamagnetic. Here magnetic behavior will be what? Paramagnetic. Okay, it will be paramagnetic. Next, bond order. Bond order will be what? You see here number of bonding orbital is how much? 2, 4, 6 and 4, 10. Okay, number of bonding orbital is 10. Number of anti-bonding is what? 2, 4, 6. So 6. So how much it will come? 10 minus 6, it will be 4 by 2, so it will be 2. That means one oxygen it will form double bond with another oxygen atoms. So this is the end of your M.O.T diagrams. Okay dear students, so chapter 4 it is completed. Okay, I request all of you to study properly. Okay, and if you have not watched the videos, earlier videos, I will share the link of this earlier videos of chapter 4 in the description box. You can see it and then you can watch from there. Okay, and I request all of you to VSCPR, hybridizations and M.O.T to practice very well from this chapter, because it is very important for your board examination. The next chapters which we are going to start in the coming days is we are going to start chapter 8, redox reactions. Okay or not? Not redox reactions. We will start with chapter 1 first. Chapter 1, let us finish up with the basic first, then we will come to the chapter 8. Okay dear students, and don't hesitate to share the video with your friends, and don't hesitate to click the button on the subscribe buttons and click on the bell icon so that you can get a notifications for your for my coming videos. And of course, if you have siblings who are studying in class 10 and all, 9, 10, for them also I have a channel called Academy Master. We are uploading the video for class 10 mathematics as well as science, so you can share the link with them as well. Thank you so much.